Okay, good morning. Today's main topic will eventually be a beautiful theorem in complexity theory called Immerman Szelepcsényi Theorem, named after the two people that independently discovered it. I really like this theorem. I think it's one of the most elegant theorems in basic complexity theory. And the gist of the theorem is that non-deterministic space is closed under complement. So we'll see a little bit more carefully what that means later. But first thing first, we have to finish up some stuff that we started last time on Thursday, where we were proving that the TQBF problem is p-space hard. And in fact, these two topics are connected, so it's kind of okay that we're doing them in the same lecture. As we'll see at the end of this proof, it already gives you some clue. Well, we already know some clue towards this about how non-determinism and its opposite are kind of equal in the context of space. Okay, so we'll spend the first little while finishing this proof that this problem, TQBF, is p-space hard. So remember, this is the problem where you're given, like, as input some formula or some sentence that looks like, for all x1, for all x2, there exists x3, such that for all x4, blah, 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 and then some formula in the x's. Okay, you're trying to decide if that's a true statement or not. And we showed last time that deciding whether such a statement is true is in polynomial space. And now we're going to complete the proof that it's hard for polynomial space, and therefore this problem is complete for polynomial space. Okay, so we just have to do the hardness part. Okay, well, it's sort of a direct proof. I mean, we've sort of seen before in the context of NP, where we showed circuit sat is NP hard, and NL when we showed ST path is hard, and P where we showed circuit evaluation is P hard. To get started, you always have to sort of prove the first hardness result for a class like directly, sort of from scratch. Okay, and then you can try to subsequently prove many other problems are hard for your complexity class. And that's how it goes for p-space too. Once you know that this problem, this sat-like problem, is p-space hard, you can prove lots of other problems are p-space hard just by reducing from this problem. Okay, but we're going to have to prove this one directly. So let's do it. Okay, so what do we have to do? We have to let any A be any language in p-space, and we have to show that it reduces to TQBF. Okay, so let A be any such language. So by definition, it's decided by some normal deterministic machine and some polynomial amount of space, which I'll call n to the little a. Okay, and so we want a reduction from A to TQBF. And because p-space is a big class, we don't mind using just a polynomial time reduction. If you really want, you can even make it log space, but we won't worry about that. We'll just do a polynomial time reduction. So I'll write down precisely what we need in a second, but let's think about what it means that M decides A in this amount of space. So as we saw last time, for each input x, let's say x is of length n, if you imagine running M on x, it has at most some exponential 2 to the order n of a different configurations. Okay, remember the configuration keeps track of the contents of all the tapes, plus the state and the position on the tape head, which is not that much. The main thing is there's a different character for each potential tape cell, of which the machine uses something like n to the a. Okay, and each one, I'm going to use this quite heavily in this proof, each is encodable by a bit string of length a log of this, so order n to the a. Okay, so the main thing encoded in a configuration is what's on the work tape. Okay, and the work tape usually can contain characters from a finite alphabet, so you might need a constant number of bits to write down each one. So okay, the configurations need about n to the a bits to write down. Okay, and so the picture, as we've seen with space-bound computation, it's good to draw these graphs where the vertices are all the configurations. Some C and some other C prime and so forth and so on. Okay, and we have a directed edge if one configuration leads to the next configuration. Okay, and since M is a deterministic machine, like there's nothing very complicated about this. It's less complicated than for non-deterministic computation. It's just every non-halting configuration has like one edge coming out of it. Where this encodes that C prime is the next configuration when you run M on X and you get to configuration C. Okay, so this configuration graph tells you about everything you might want to know about M's computation on X. And there's one specific start configuration that just has X written on the tape, and the head is at the beginning, and you're in the initial state. And we can also, as we saw a few times, we can assume without loss of generality that there's a unique accepting configuration. Okay, because we can modify M a little so that right before it accepts, it like erases the whole tape and moves the head back to the beginning of the tape, and only then accepts. Okay, so that modification doesn't really change much. And then it's nice because we have a unique accepting configuration. And so what this all means is that this string X is in A if and only if M of X accepts, which is if and only if there exists a path in this configuration graph. Let me call this configuration graph G. It depends on M and X. A path from this C start configuration to the C accept configuration in G. Okay, so remember what we're trying to do here. We're trying to show that A reduces to TQBF. So we need to build a polynomial time reduction, R, that takes as input a string X. So this is what we need to do. R that takes a string X and outputs one of these formulas that's like for all exists, etc., which will depend on X. So maybe I'll write it depends on M and X. Okay, such that, well, X is in A if and only if this formula is true. That's what it means to be a reduction. Okay, and we just saw that X is in A if and only if there's a path from the start configuration to the accept configuration in this graph. So the way we can phrase it is such that there exists a path C start to C accept in the graph if and only if phi is true. Okay, so R should look at X, and it should build some formula which expresses the statement that this path exists. Okay. Any question about this? So if we have this, then we have this correct polynomial time reduction. So I'm going to describe to you how this reduction works. And basically, I'm just going to describe kind of in words or mathematically what this big phi is. I'll just sometimes just call this phi. And sort of the key to understanding the proof will be to show that it's not too long, that it has polynomial length. Okay, that's certainly better be true because this polynomial time algorithm has to output it. So it better at least have polynomial length. Now, it's more than that. I mean, I also need that there's a polynomial time algorithm that can generate it given X. But that's going to be kind of easy. Like when I finally describe phi, it'll be pretty simple. It'll have a pretty simple dependence on X. Like nothing wacky will go on, and you'll sort of easily believe that R can compute phi from X in polynomial time. So the fact that phi is polytime computable will be straightforward. Okay, I guess if it's, if it If it seems not straightforward, feel free to ask a question, but I think you'll see that that's not the major issue. In fact, by the way, this is going to have length order n to the 2a, just as a spoiler. OK. So good. I have to describe this formula phi, or this sentence phi, that captures the existence of this path. Now phi, it's going to look something like this. For all, I don't know, z1. It's actually going to start with like a lot of for alls. And then like it actually is going to have a lot of there exists. I don't know. I'm just making up letters here. W1. There exists W2. And in fact, all these big blocks of like for alls and there exists, these are going to have length like order n to the a many variables. And the reason is they're actually going to be the bit encodings, or stand for the bit encodings of configurations. OK, so in TQBF, the quantifiers are over variables that represent 1 bit. But I want to kind of get to the stage where phi is saying stuff like for all configuration C, there exists a configuration D, such that blah, blah, blah. So we're just going to remember that every configuration is encodable by a bit string with like something like n to the a bits in it. OK, so really it's bits, but I'm going to start writing things like phi is for all C1, there exists a C2 such that, and then some formula that involves these things. OK, and this is just shorthand for all like order n to the a variables that are encoding C. OK? OK, so it's a bit tricky. I mean, uses some nice ideas, this reduction, to figure out how to get this TQBF formula that encodes the existence of this path. So we're going to go through 3 ideas, and finally, like the third idea will work. OK, so I'll warm you up with idea 0, idea 1, and the final idea 2. So let's start with idea 0, which has a major flaw in it, but it'll get us warmed up. OK, so idea 0 is we're trying to have phi say something like there exists a path from C start to C accept. Well, phi can have exists in it, so like let's just use a bunch of those. So idea 0, which will get us started, but will not be a great idea, will look like this. There exists C1 such that there exists C2, such that there exists C3, such that, and then, well, we'll do this for some amount of C's. Let's say L. Come back to what L is in a second. Such that, OK, and now we have to put a formula down. And really, we're just trying to express the idea that, this is the path from C start to C accept. Like these C's are the path. OK, so we have to express that. So what we're going to write for the formula part is, let me write something, and I'll explain it a bit more in a second. All right, phi yields C start, C1, and phi yields C1, C2, and phi yields C2, C3, and dot, 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 and up to L, and then maybe after L, I'll stick on C accept at the end. OK, where phi yields is a formula, I'll say this now, but somehow express the condition that, C2 goes to C3 in this graph. OK, so it states, from C and C prime, so that stating that, C to C prime is an edge in the graph. OK, well, I mean, I say that phi yields is a formula with these properties, but we have to ask ourselves, does that like make sense? And I claim that such a formula exists. OK, so I claim phi yields really exists. And let me just not write anything, but I'll talk about this claim. You know, I want to say that there's some formula that encodes that this is the encoding of the configuration that follows from this configuration in M's computation on X. OK, so I mean, you know, C is a bunch of bits that represent mostly the work tape of M and also the state that M is in and where the head is. And C prime is like another bit string that encodes this in some natural way. And it's kind of a lot like this like Tableau business. Like, you know, maybe C looks like this, and maybe it's got some symbol for the state in here. And it's otherwise, it's got like work tape stuff, and like C prime is some encoding of this. OK, and the formula just has to check that like all of these kind of pieces are consistent. You know, these sort of triangles. You know, this thing is usually just equal to this thing unless the tape head symbol was up here and so forth. So, you know, I don't want to get into this much more, but it's a very simple computation to check that C prime is exactly what follows from C. It depends on M. And you can encapsulate that with like a little formula that checks that appropriate bits are equal to each other or that they're equal to some function of these bits. So how believable does that sound? Does it sound OK? OK, I hope it's OK. We saw actually many times that, like, you know, the proof of Cook-Levin, there's like a circuit, a little circuit piece of gadgetry. You like add together all these, you know, triangles, and you can also make a formula. OK. So I suppose also we need that it's easy to construct, polynomial time to construct, because if this idea 0 was the final idea, which it's not, you know, the reduction would actually have to write down this phi, but it can do that. And actually, for full details, if this were the final solution, R would have to take X and output this formula for some value of L. That's going to be the problem in a second. For some value of L. So it has to be able to construct phi yields. And I guess it also has to be able to write this down. That's the part that actually depends on X. C start is the only thing depending on X. Right, because C start is, well, it's really the encoding of the configuration that looks like, you know, the tape head goes here, and it's state X0, Q0, and then you have X on the input tape. OK, but it's a simple algorithm to like write down the encoding of this start configuration given X. OK, so all is good with idea 0 except for one flaw, which is, well, what is the flaw in some detail? Yeah? It's
not taking into account the lengths of the path.
Yeah, well, in order for a sentence like this to correctly capture the statement that there exists a path from C start to C except in this graph, how big would L have to be? Yeah?
You could run to the NPCo time, so you have to count all those paths.
Yeah, I would prefer to say that it could have that many configurations, but yeah. So this only correctly captures the statement. I mean, this captures the statement that there exists this path, but only if L needs to be, you know, like the number of vertices in the graph, right? Because a priori, I guess actually time does make the difference. A priori, I mean, you know, the path from C start to C except could, you know, go through all the configurations, or it could at least, you know, take as many steps as the running time of M. But unfortunately, that's like exponential, right? The number of configurations is exponential. It's 2 to the order of n to the a. Yeah, so you're right. I guess it's upper bounded by the running time, but the running time could be exponential. So this would be fine if you made L exponentially large, but then, I mean, we definitely didn't achieve this. You know, it'd take the polynomial time algorithm R, well, it would take the algorithm R exponential time to write down this phi. Okay, so it's kind of a good start, and I put it down there so I get the chance to talk about this phi yields thing and stuff like that. But it doesn't work. And you can see, I mean, it was not the smartest move because TQBF has this glorious power. It can have there exists and for all, and we only use there exists. So we got to use more power. OK. So now we'll come to a good idea that almost works. And the good idea is one we've seen before. It's basically the idea of Savety's theorem, okay? Which is the idea that you can express the existence of a path from one vertex to another by saying, OK, there exists a midpoint such that you can go from the start to the midpoint and from the midpoint to the end, and kind of recursively build up your expression of the existence of the path in that way. So what we're going to do in aid of finally building this capital phi is we're going to build a very general formula or a sentence, which I'll call phi sub k. And this formula will be parameterized by two configurations, C0 or C1 and C1, which is true if and only if there exists a path from C0 to C1 of at most 2 to the k steps. Okay, this is exactly like the idea that was in Savety's theorem. So this will be our main task. And if we can accomplish this, then we're in great shape. Then R will finally just output. So what should R finally output? If it knows how to do this in general. Yeah, so, well, phi sub, order n to the a of
C stack C.
Yeah. So I'm going to show that this R, given any k and the description of any two configurations, can build this sentence that has this property. And what it really wants to know is if you can get from start to accept, and at most, the upper bound on the number of steps you need is 2 to the order n to the a. OK, so we want to show how you can build this sentence, but still we want to make sure it's not too large. OK, so we need to make sure that this is still like poly in n or poly in n to the a length. OK, so we can build it inductively, and it'll be like Savety's theorem again. We'll start with the base case, which is k equals 0. So phi 0 of C0, C1. This is supposed to be a formula which is true if you can get from C0 to C1 in at most 1 steps. So at a slightly high level, what should this formula be?
Yield C1, C0, C1.
Say again?
Yield C0, C1.
Mainly, yeah. So it should be this formula, phi yields C0, C1. There's a little bit more.
Or C0, C1.
Yeah, or, let me put in quotes, C0 equals C1. Well, I put it in quotes because, you know, this is really like n to the a bits, and this is some other n to the a bits, and you have to say that they're equal pairwise. So it's like the first bit of this equals the first bit of this, and the second bit of this equals the second bit of this, and etc. And, you know, to express the two bits are equal, depends if you allow this in your formula or not. If you do, it's fine. Otherwise, you can, I don't know, write this. Okay, anyway, you can write a formula that says this bit string equals that bit string. Good, so this is correct. And what size does it take? This thing takes order, I think, n to the a. We kind of talked about that. Maybe polynomial in that. We didn't look into it too carefully, but I think it's even order n to the a. This also takes about order n to the a amount of ink. So that's good. Things are looking okay so far. Any questions? Okay. Okay, and now we come to the Savety idea for the induction. So in general, phi k, C0, C1, well, it's going to express this idea that, you know, you can reach C0 to C1 in at most 2 to the k steps if there's some middle point configuration, which you can get to in 2 to the k minus 1 steps from C0, and you can get from there to C1 in at most 2 to the k minus 1 steps. So the idea is we'll write phi k, oops, sorry. I should mention, by the way, this has no quantifiers. This is just a plain formula. That's fine. But now we're going to use a quantifier. So there exists a C mid such that phi you can get from C0 to C mid and at most 2 to the k minus 1. And you can get from C mid to C1 and at most 2 to the k minus 1. Okay, so this is, I claim, correct. It correctly encapsulates the statement that there's a path from C0 to C1 of length at most 2 to the k by the Savety idea. And it's a good idea, but unfortunately the size, when you like actually expand this all out, like when you literally build phi 1 by writing this down and plugging in phi 0, and then you build phi 2 by literally writing this down and plugging in what you get for phi 1 and so forth. Unfortunately, the size turns out to be exponential again. Let's even see why. Right, like how much space does this take? Well, this is another like order n to the a bits, because that's how many bits you need to write this down. You know, these punctuation marks are constants, but we get 2 times the size of the one smaller phi. So the size of phi k, if we just work it out, okay, it's order n to the a plus 2 times the size of phi k minus 1. And this is the base case. And you can see that's not very good. I mean, okay, it's a little recursion that maybe you have to think for yourself about how to solve it. But you see at the kth level, you kind of have 2 branches out. And then they have 2 branches out. And they have 2 branches out. And so if you're at size, you know, for phi k, you eventually kind of have like 2 to the k leaves. And even those leaves are costing you n to the a. And actually, all the intermediate nodes also cost you n to the a. So if you solve this, you get that the size of phi k is something like order 2 to the k times n to the a. And that's bad. Because the final thing that R wants to output, it needs to take k to be like n to the a. So then this will again, order n to the a even, so this will again have size like 2 to the n to the a. So it's exponential size. So it's a cool idea, but still to implement it, the size you need would be exponential. But there's going to be a trick that saves this idea. But let me ask if there are any questions about that. OK. Well, we need to come to final idea, which is idea 0, or idea 2. And in some ways, the idea is like we kind of screwed up a little bit because we have this factor of 2 in our recursion. Like we paid for both the recursive calls in terms of size. It's a little bit how, like in Szelepcsényi's theorem, it would be dumb of you to like use different space for the 2 recursive calls. Like somehow the one last thing we have to do is sort of like reuse the space in a weird high-level way. Maybe that'll make more sense when I show you the actual idea. So here's the idea for the idea. The idea for the idea is this. Imagine in life you have like a really long formula called blah. And in fact, it has like a parameter. And you would like to express that like blah with parameter 0 is true and blah with parameter 1 is true. And imagine blah is like super long, so you have to like write it all out and your wrist hurts. And you have to like write it all out again with like 1 instead of 0. Well, you can save 50% on ink. The following observation. This is the same as saying like for all j in 0, 1, it's not much of a for all, but for all j in 0, 1, blah sub j. And you know, these two statements, this is a high-level picture. These two statements are like the same in meaning. But like you saved yourself basically 50% ink, right? Because you only had to write this extremely long blah thing one time, plus a few more characters. OK? So that's exactly the idea we'll use to improve upon this. Like practically the same thing. You just want to like say 2 things are true, but we want to use a for all to save on writing this twice. So to implement that, you have to think for like 5 seconds or 5 minutes. Let me not make you do that. I'll just write down the answer, and then we'll all agree that it works. So here's the final kind of solution. Phi k of C0, C1 is going to be same thing. There exists a C mid. OK? And then such that for all d and for all d prime, these d and d prime are also configurations. Let me just write a gigantic formula here, and we'll come to like it. D prime equals C0, C mid, or D prime equals C mid, C1 implies that phi k minus 1 of d prime. OK. This is the formula that works. So what's going on here? It's the same as, I mean, you should compare it to this one. It's saying the exact same thing in a funny way. It's saying the exist C mid is the same. And it's just kind of doing the 2 cases here. It's saying if d and d prime are any pair of configurations such that they're either C0, C mid, or they're C mid, C1, then indeed, you know, phi k minus 1 should hold true about d and d prime. So this is just like a funny ink-saving way to express the same concept as over there. And this is all like, it's a little bit shorthand, but I mean, this is saying that d equals C0 and d prime equals C mid, or d equals C mid and d prime equals C. And all those checks are similar to like these checks. I mean, you can write down a very simple formula that checks them. So this whole thing is like one big Boolean formula involving all the bits of d and d prime and C mid and C0 and C1. That exactly captures what we want. Does it make sense? OK, so what I'm saying is that this whole thing is finally correct. And this is the end of the idea. We're going to do the space analysis to finish it. But R finally outputs like the formula phi, where k is n to the a, of c star and c except. And it builds it inductively according to this recipe. So it writes down all this junk. And then it has to inductively write down the associated junk for this and the associated junk for that, and so forth and so on. But now you see it's kind of an induction with like no forking. Like it's almost like linear. So let's figure out the size analysis. What is the size of phi k? Well, you have to write down like all of this junk and the parenthesis at the end. This is like a finite number of 5 or 3 configurations, which are order n to the a bits, and some formulas involving them. So let's order n to the a bits plus the recursive size of phi k minus 1. Okay, and this is a very pleasant recursion because it's going to give you that the overall size of phi to the k solves down to just order like k times n to the a. And that's great because that means the size of the final output of R, which is written up there, well, it's basically k is going to be n to the a. So it'll be order n to the 2a. And that's basically it, right? This is polynomial. And furthermore, I hope you agree that this part is OK. I mean, not only does R have enough time to write down the answer, it can also sort of easily compute the answer in polynomial time. It just has to follow this simple recipe. OK, any questions? Cool. OK, so we've actually finished that theorem now, that TQBF is p-space complete. Oh, it's no longer up there. OK, and I want to move down to smaller space classes for the final theorem we're going to prove about space, which is the Immerman Szelepcsényi Theorem. And actually, one interesting thing about this proof we just did was that, it relied on this configuration graph, which is a very simple graph where you have like one out edge for each configuration. That's because m was deterministic. Now, if m was non-deterministic, actually the whole proof would not be much different. I mean, you still have, the only thing is you'd have like 2 edges coming out of each configuration. You can still easily write down this phi sub yields thing. And so actually, if you inspect this proof, you can use it to show that TQBF is complete even for non-deterministic polynomial space, which in turn implies that non-deterministic polynomial space equals deterministic polynomial space, which we already saw using Savety's theorem. And p-space is also closed under complement. I'll remind you a little bit about these things, which means that non-deterministic polynomial space equals the complement of non-deterministic polynomial space. And this theorem that we're going to spend the rest of the class proving is that exact same theorem, but for log space instead of polynomial space. OK, so that was a lot of words, but let me just remind you, we actually already saw before, and you can use this proof to see again that non-deterministic space, polynomial space, is the same as co-non-deterministic polynomial space. In fact, they're both equal to p-space. And this is kind of funny because it's something that we don't think is true in the context of polynomial time. We don't think that NP and co-NP are the same thing. But for space, it's true. And you may hope for a scaled down version of this, which would be that NL equals co-NL. Remember, the co of a class is like all the languages whose complement is in that class. And whether or not you can have this was actually, in the olden days of complexity in like the 80s and stuff, this was like an open question, and people believed that the answer was no, that this was false. And then two people independently, Neil Immerman, who was a pretty well-known CS researcher at the time, and Szelepcsényi, who was like a totally unknown master's student in Slovakia, in '88, they kind of surprised everybody by independently proving that this is true. So that NL equals co-NL. And that's what I would like to prove in the rest of the class. And let me just sort of get you a little bit more acquainted with it, and then I'll make a couple of remarks. What does this mean? NL equals co-NL. Well, OK, you need to show, I'll say some statements that it's equivalent to. So this is equivalent to the statement that ST path is in the complexity class co-NL. So why is that? Well, we know, the one thing that we know about NL is that ST path is a complete problem for it. So if NL equals co-NL, then certainly ST path, which is in NL, is in co-NL. On the other hand, if like the hardest problem for a class is in a certain other class, then that means the whole class is in that class, right? So I mean, everything in NL reduces to ST path, log space reductions, and therefore this implies that all of NL is in co-NL. Well, we actually want that they're equal, but once this is true, you get the other inclusion by symmetry. Or maybe I'll make this a homework. It's very simple to work out, but you can work it out. And here's another thing. This is also equivalent to, I mean, what does this mean? Literally, by definition, it means the complement of ST path is in co-NL. So is in NL. I'll stop shuffling symbols around in a second. What is the complement of ST path? This is the problem, given a graph, a digraph G and S and T, you want to say yes if there isn't a path from S to T in G. Okay, we want to say that that problem is in NL. And that's a surprising statement. We have two definitions of NL, you saw from the homework. One is with terms of non-deterministic Turing machines. But these non-deterministic Turing machines are always geared exactly for proving like there exist type statements, right? I mean, if your problem is to decide whether a certain thing exists, a non-deterministic machine just uses its branching to like try all possibilities and check them. Okay, it's like very bad for trying to show that something doesn't exist. Or similarly, we also had this kind of verifier definition of NL, just like we had one for NP, where you kind of get like a certificate that can be checked in log space. And like, it's hard to imagine like a certificate that will convince you that there's not a path from one vertex to another in a graph. So that's exactly how we're going to think about it in the rest of the class, like certificates. Easily checked certificates that there's not a path from S to T in a graph. Okay, so that's kind of the weird thing that people didn't expect was possible. Any questions at this point? I mean, there's a lot of, yeah.
So when we prove that we proved NL equals co-NL through this indirect method, so afterwards, were we able to find like valid certificates that showed there doesn't exist a path, or that's still
Yeah, no, the way we're going to prove this by really defining like certificates that a log space verifier can check for non-existent paths. That shows that the complement of ST path is in NL, which shows kind of by definition that ST path is in co-NL. And like this is like the hardest problem for NL. That's what we know. So that is the reason that NL is in co-NL, and that also implies that NL equals co-NL. Now let me make a couple. Let me make a very quick remark. Once you have this, we're not going to do this, but you can also easily show that n space fn equals co-n space fn for all fn greater than or equal to log n. So basically, like log space is the hardest case, and this proof like scales up. Don't worry about that too much. Yeah, so before we get into this, let me make a couple philosophical remarks. Why to care about this theorem? I mean, one, if you really love complexity theory, then it's a great theorem. It's kind of surprising. The proof, as you'll see, is like very elegant. So like, I really like this theorem. On the other hand, if you're just a person, you're like, I'm graduating in 6 weeks, and like it's not even 10 a.m., and like I'm proving theorems about co-non-deterministic log space. Like, what am I doing with my life? No, it's kind of cool because here's, I guess, one reason I think you should. It's indirect, but you should care about it. Like, once you know this, it makes it a lot easier to prove that problems are in NL. In fact, I posted on Piazza. I didn't realize this until kind of too late, but anyway, I messed around with you because of it. Once you know this, it's like, for example, a lot easier to solve, I think, homework 2, that like showing graph connectivity is in NL. Because like now you like know more powerful facts about NL, and you can like, you could try to show this in co-NL, or you can use like subroutines and stuff. So that's why I said you cannot use this fact in solving that homework problem. But that's one cool, reason to care about this theorem. It can help you show problems in NL because it shows it's the same as this bigger class or this alternate class. Why would you want to show the problems are in NL? That's actually a little bit related to problems 3a and b on the homework, that thing about integer partitioning. I think sometimes it's easier to show a problem is in NL than to show it's in P, which doesn't seem possible at first because NL is a subset of P, so it should only be easier to show that things are in P. But I think from 3 you can sometimes see that psychologically it's actually easier sometimes to show things are in NL. And that helps you show some problems that are solvable in polynomial time. In fact, I didn't get a chance to talk about this, but NL is also in this class of highly efficient parallel algorithms called NC. So it's another reason to motivate you to show that problems are in NL, which is easier to do once you know it equals co-NL. Okay, so that's my philosophy about NL equals co-NL. But also, it's a great proof, so I want to show it to you. Okay, so whenever you're trying to show something is in like a class that starts with n, you kind of have two choices. You can do it by designing a non-deterministic machine, or by designing kind of this like sort of certificate and verification routine. I actually think in life it's almost always easier to design the non-deterministic machine. Maybe you don't feel that way because you don't like non-determinism so much, but I think once you eventually get used to it, it's usually easier. But I think for this problem, it could go either way, but I think it may even be easier to show the verification style proof, so that's what we're going to do. So what I want to show you, this is all equivalent. I want to show you that there exists a log space verifier that can check when like a graph, an S, and a T are not in ST path. Okay, that like that there's no path from S to T in a graph. Okay, and that's kind of like the surprising thing, that you get this like super easy to check certificate that this path does not exist. So let me draw the picture of this verification setup to remind you of the story. So the input graph is the graph and also S and T, and they're hanging out on a read-only input tape. You have to cast your mind back to the previous homework where you're talking about the verification definition of NL. And we're going to design like a certificate system where the certificate goes on this read once tape. So the verifier can only scan it from left to right. And the verifier is this log space machine here, V. It has a tape head for the input. It has this tape head for the certificate that can only go right. Okay, and it also has tape head for one or more work tapes, where it can read and write, and these use only order log n bits, or space. Okay, so this is the picture of the story we're going to tell. And what I'm going to tell tell you now is the structure of the expected certificate. This is how, I mean, at a high level, these like verifier type proofs always go, right? I mean, if I'm going to show you that 3 colorability is an NP, the main thing I tell you is like what the verifier expects to see in aid of checking that the graph is 3 colorable. Right? So I'm going to tell you what the certificate should be in the case that the input is in the language, i.e. in the case that there's no ST path. And I'll explain how the verifier can highly efficiently, like with only this much space, sort of check the certificate and become convinced at the very end that, oh yeah, it's really true. There is no path from S to T in the graph. OK? OK. Great. We have lots of time. Well, we have just about the right amount of time. OK, so I just need a little bit of notation to explain what this certificate should look like. Right? I mean, if you're designing certificates for the complement problem that there is a path from S to T, then of course the certificate will just be like the path. The verifier can check that each consecutive pair of vertices along the path is really an edge, and then it's happy. But we've got to certify the opposite. Okay, so a little bit of notation. Given the graph, I'm going to let capital R sub L be all the set of vertices reachable from the start vertex S in at most L steps. Okay, this is for L between 0 and N. N is the number of vertices in the graph. And actually, the main reason I write it is what I really care about is what I'll call little rl, which is the cardinality of this. This little rl is somehow the key to the whole certificate system. For each L, it's a number between 0 and N, which is the number of vertices reachable from S in the graph in at most L steps. Now, certainly, these are numbers that the verifier cannot obviously or easily figure out for itself. It's a complicated calculation. This is just a poor little like log space verifier. But these numbers are going to play a key role in the certificate. But in fact, as it's going along and checking this certificate, it's going to eventually learn and become convinced of all of these RL values. That's going to be very important for the whole system. By the way, what is R0? It's a set of size 1. S, yeah. It's just S, and so little r0 is 1. And that's a little base case. OK, so let me tell you, let me start to drill down on what this certificate is supposed to look like in the case where really there is no path from S to T. So it's going to look like this. It's going to be divided into pieces. And I'll kind of give them high-level names. It's going to start with a certificate for the value of R1. I'll say what that means as we go along. And then the next part is going to be a certificate for the value of R2. And then the next part is going to be a certificate. These are just all concatenated together for the value of R3. As you may expect, it goes all the way to a certificate for the value of Rn. And then the last thing is going to kind of be the main thing, which is a certificate that T is not reachable from S. Okay, so this is the thing that the verifier really wants to be convinced of. But like, it's going to have the prover or the certificate convince it of a lot of stuff before it's sort of ready to accept a proof that T is not reachable from S. So remember that the verifier is only able to process this from left to right. It cannot go back. But like once it kind of processes all this and does some checks, at this point, it's going to be like, OK, verifier, or OK, prover, like, I'm with you. I totally agree on what the value of R1 is. OK, and then after it reads this, it's going to be like, all right, I totally agree on what the value of R2 is. And after it reads this, it's going to totally agree on what the value of R3 is. Up to here, it's going to totally agree what the value for Rn is. And now it like knows what Rn is, and that's going to help it become convinced of this part. Now, I said that, like, you know, at this point, it's going to totally know. It's going to be like, OK, prover, you got me. I totally agree on what the value of R3 is. But one thing is, it's not going to remember all these R values over the course of this processing, because it doesn't have enough space. Each of these R values is a number between 0 and n, so you can write it down with log n bits. So you can certainly save that on a work tape. Well, you cannot save all of them on a work tape, right? There's n, or n plus whatever, n of them. So as it becomes convinced of these values, it can maybe write down one of them or two of them, but it cannot write down all of them. OK, but the good thing is, in order to become convinced of the value of R3, it's really only going to need to remember what R2 was. And to become convinced of what R4 was, it's really only going to need to remember what R3 was. So this is a key point. Let me write this down with a star. After V processes the certificate for some RL, it's only going to retain, well, L and R of L on its work tape. Okay, L is also a number between 1 and n. So like at this point, after it finishes this, it's going to sort of have written on its work tape like, OK, I just finished getting convinced of the third value of R. That 3 is some log n bits. And the value of that R, R3, was some number, which it's going to store. And it's only going to, you know, it can just erase all the other space or reuse all the other space. It's only going to remember these things when it tries to get convinced what R4 is. OK. OK, any questions so far? I mean, it's still quite a big mystery, I mean, how the certificate is going to look like. But this is the overall high-level picture. OK. So I actually want to start at the end. So I'm not going to tell you just yet how this certificate can convince the little verifier of all these R values, and in particular the value Rn. But let me assume it can do all that. And then I'll tell you what the verifier expects and what it does after it's processed up to here. OK, so suppose we got to the part where it's now convinced of Rn. OK, so it now knows exactly how many vertices are reachable at all, because Rn is, if you're reachable at all, from S. And now it wants to be convinced that T is not one of those vertices. OK, so here's the idea. What certificate would convince V that, what does it really need? It needs that T is not in this set capital Rn. OK, well, let me draw it for you. It's going to be like another high-level plan that looks like this. So the certificate of T not being in Rn is going to look like this. I'm going to not write things in generality, but I'll write like specific numbers to just give you the idea. So it expects the first part of the certificate to look like something like this. A path from S to some other vertex. Let's say maybe vertex number 2. And then it expects the next part of the certificate to look like a path from S to some other vertex, maybe vertex number, I don't know, 5. And then it expects the certificate to look like another path from S to some other vertex, I don't know, maybe vertex number 6. And then a bunch more of these, and then finally it'll end with, the certificate will end with a path from S to some other vertex, maybe vertex number, I don't know, n minus 1. The high-level idea is that it knows Rn. So like the high-level idea is it's going to check that all these certificates are cool, that they kind of show that number 2 is reachable from S, number 5 is reachable from S, number 6 is reachable from S, number n minus 1 is reachable from S. And then if they're exactly little rn of those certificates, and T was not one of the endpoints, then it becomes convinced that T is not reachable from S. It's like the certificate or the prover is like sort of convinced it of the identity of these vertices in capital Rn. Okay, this is all predicated on it being like truly convinced of the value of little rn. We're going to get into more detail, but yeah? Yeah, so it also has to, it's still not so easy to do this because it only has log space. So like it has to check that it's not getting cheated in some like fishy way, like maybe this was 2. And then couldn't really check that because like then it would kind of be getting cheated, like the certificate it's like telling it 2 more than once. So it has to be able to catch those kinds of cheats. So let me write down all the things that the verifier checks, or how the verifier works, and we'll kind of agree that this works. So the verifier is going to check a bunch of things. So it's processing this from left to right. It cannot go back, but it has log n workspace. And it also all the time can go and look around at G, the structure of G. So it's going to check a bunch of things. It's going to check that each path in each of these pieces is really in G. And this is something that we've seen a couple of times, where it just goes through the pairs of vertices one by one and spends a bunch of time looking up whether or not there are actually edges in G. Okay, so it needs very little space for that. It needs, log n space just to write down on its work tape, maybe the copy, the identities of a couple of vertices. Okay, those are all log n bits. So it can really, tick along this purported path and really become convinced that, okay, it started with S and it ended at some point, and this path was really in the graph. So okay, it becomes convinced that this vertex is reachable from S. So it's also going to check that there are exactly little rn, paths presented. And how does it do that? Well, it just keeps a counter on a separate tape of the number of paths it's checked. Okay, and there's at most going to be n of them. So let's log n bits. Okay. So there's 2 more things to check. One, which looks like the main check, but there's one important thing left, is that it checks that T is not among the endpoints. Okay, how does it do that? That's easy. I mean, you can just sort of save each vertex that it's reading on the certificate, and then when it gets to the end of one certificate, it's like, oh, hold on, let's check if the last vertex that we were talking about is T or not. So I can go back and look in the input and check whether it was or not. Okay, so it's going to check that T is not among them. But it's not quite done, and this kind of gets at what William was saying. At this point, like the only thing it's really convinced, if it only did these checks, it could be cheated a little. If, for example, these endpoints, some of them had repeats. Because the idea of the proof is that the certificate is supposed to be presenting exactly the set of vertices that are in capital R sub n. But if like the repeats, then it would be cheating you by presenting fewer vertices and that are in Rn that are really fewer than all of them. That was grammatically a total fail, but it's okay. So how does it handle that? Yeah.
You could say that it has to paths in some kind of order, and then you can like hold on to what the previous vertex you saw was. So you, like for the first thing, you can say I saw vertex 2, and then if the next one is equal or less than 2, then you say it's a bad certificate.
Exactly. So it's it was not like an accident that I wrote like 2, then 5, then 6, then something that's close to n. So it really expects that not only does it get little rn paths presented to it, but like the endpoints should be listed in increasing order. I have to take a little bit of thought about how I can check this. I mean, you said it, but it checks that the endpoints are in strictly increasing order. So actually, if it can check this, then it means the certificate can't be cheating it by like presenting the same vertex more than once. Like it really has to be giving little rn distinct paths. And it cannot do this by like remembering all the endpoints, because that's too many. But in order to check that, it just has to remember the last endpoint, right? So like it's processing around here, it gets to the end, and it's like, OK, I'm going to put in for this last check, I'm going to write down 5 somewhere. And then when I'm doing this, and I get to 6, I'm going to check that, OK, that this 6 is really bigger than this 5. So like locally, it was increasing from here to here. And then it can forget 5 and just remember that the next one was 6. And then when it checks this, it checks that the endpoint is some number bigger than 6. And then it can forget 6 and just remember that endpoint, and so forth. And that's actually it. So this it can do by retaining, always just the last endpoint. Okay, the previous endpoint only. Okay, and that's actually it for what this certificate is supposed to be and how the verifier checks it. All predicated on it was able to get up to this point and like totally agree what the value of little rn is. Any questions? OK, so now, finally, I have to tell you how it figures out these little r's. OK, and I'll just have to tell you like kind of how to do one step. So let's say we're here. Let's say this is RL. We just finished processing all this. We're totally convinced of what RL is, how many vertices are reachable from S in at most L steps. And now we have to get convinced how many vertices are reachable from S in L+1 steps. And we're only retaining, well, the knowledge of L and what R sub L was. OK, so the last piece of the puzzle, assuming RL is certified, how does V certify RL+1? Or more accurately, in the case where there really is no path from S to T, so there should be a legitimate certificate that certifies it, like what should the certificate say in the RL+1 block, and how does the verifier check that? So it also has like a substructure that we need to drill down into. So what is this certificate for RL+1 going to look like? Inside one of these boxes, it's going to have a lot of parts. And again, I'll kind of do sort of an example. It's going to look like a list of certificates, one for each vertex in the graph, presented in order. And it's going to look like this. It's going to look like something that's like vertex number 1 is in RL+1 because, and then some stuff. And then like another piece that says vertex number 2 is in RL+1 because some stuff. Then it's not like every vertex is in RL+1. So like perhaps vertex 3 really isn't in L+1. So it's going to look like vertex number 3 is not in RL+1 because, and then some further certificate. And vertex number 4 either is or isn't, maybe isn't, with some certificate. And like a bunch of these things, all the way out to vertex number n is or isn't in RL plus 1 because of some stuff. By the way, you should kind of be checking that all these certificates are of polynomial length. It'll actually be implied by the fact that the verifier runs in log space, but it's good to check it anyway. Anyway, these certificates has like one block for every vertex, and they're presented in order. And what's the idea? Well, the verifier is going to proceed through all these certificates, and it's going to really try to check this claim. I haven't filled out this squiggly stuff. But if it can do that, then it's in good shape, because it will just count the number. Like if it becomes convinced of all of n of these claims, then it'll just keep a counter of how many times it became convinced that a certain vertex was in capital R sub L plus 1. Okay, and then that counter at the end will tell it little r sub L plus 1. So if I can fill in these squiggles to explain how it can be convinced of either a claim that looks like this or a claim that looks like this, then we'll be done. So let me write this. Yep?
So we can keep a counter to, like when we have a certificate for RL plus 1, we can keep a counter to like what RL is. And then we're using that to check the last certificate, that T not equal from S.
Yes.
There would be, you would need n such counters then.
Well, this is a key point. So like once you get convinced of what RL plus 1's value is, you kind of forget RL.
Oh.
You reuse the space. So you only ever keep track of the last R value that was certified to you. And like here, we only needed to know R sub n. And we'll see it didn't show up yet, but like for certifying each of these claims, we're going to only need to know R sub L. In fact, we're only going to need to know R sub L to be able to check the claims that it's not in RL plus 1. It's going to be easier to check these kind of claims. Okay, so before we get into that, what does the verifier do overall here? Well, it's going to check a few things. It checks that, each vertex, number 1, number 2, all the way up to number n, appears and has a claim about it. Okay, and that's actually similar to the check that we saw above, that the vertices were in strictly increasing order, right? It just checks, for each one, it keeps a separate counter, like I'm supposed to be on number 1, now I'm supposed to be on number 2, now I'm supposed to be on number 3, and it checks that. And it counts the counter, how many, vertex I is in RL plus 1 claims it sees. Okay, and that actually at the end, that gives RL plus 1. So the last piece of the puzzle is it really must be able to successfully check and become convinced of each of these claims, either its in claim or an its out claim. So it checks all the, because blah, which I haven't specified yet, parts of the proofs. So now, the very last step, we're getting towards done, is to explain how you can have a certificate for each of the two kinds of claims. The claim that a given vertex is in RL plus 1, which means it is reachable from S in at most L plus 1 steps, and the opposite claim that it's not reachable in at most L plus 1 steps. Okay, so the former kind is easier. So let's say one of these things is a claim that looks like vertex number 8 is in RL plus 1 because, okay, and we just have to decide what to write here. And really this means that S can go to 8 in at most L plus 1 steps. Okay, so What should go here? Yeah?
Just the bottom length of this one. Sorry,
Yeah.
this one.
That's right. This is the easier one for NL type computations to become convinced that there is a path of this length. So the certificate will just be, this sub-certificate, it'll just be the path, or a path written out of length at most L plus 1. Okay, and so to check this, we've talked about it before, but just verifier checks. It's a legit path. So every pair of consecutive vertices, it has to go back and look at the input G to check that it's really an edge in there. Okay, and then it also has to keep a counter to check that the path length is at most L plus 1. That's another log n bits. Yeah?
If our certificate, this part is like just including this whole path, like why do we need like R1, R2, R3, R4? Why can't, if we're going to include like this whole path, like why can't we just say Rn and like that's?
Excellent question. This is what I said in words back here. There's two kinds of certificates here, the ones that the vertex is in capital RL plus 1 and the ones that it's not. And for these ones, we don't need to know R sub L. Although I don't know why I pointed at RL here. I should really point it at like one of these. As you see here, we don't need to know RL L. We need to know L. Well, that's fine. But like the final last linchpin is like what these certificates look like for here. And for these guys, you're going to need to know R sub L. But only R sub L. Okay, great. So finally, we have to explain what kind of certificate could we have here for a claim that looks like vertex number, let's say 9, is not in RL plus 1. And if you think about it, this is almost the same as this. Like we're trying to get like a certificate or a proof that some vertex 9 is not reachable from S in L plus 1 or fewer steps, which is kind of like the same deal we had with T. And similarly, it's going to be enough to know R sub L. So I don't have too much time. I'll hurriedly write it. Hopefully, if you don't catch everything I'm going to say, let me just say it's very similar to this. So this piece here will tell, or you might even think of it as reminds, V, all the vertices in R sub L. Okay? And it's going to do that by having all these more things that look like S goes to vertex number 1 in at most L. And it's going to have another piece that shows, S goes to vertex number 7 in at most L. Okay? And it's supposed to have exactly R sub L many of these. So as before, V is going to check that the endpoints are listed in increasing order, strictly increasing order, which it can do in log space, as we saw. And it's going to check with the counter that there are exactly R sub little l of them. Okay, so here's where it needs to know and really be convinced of what RL's values are. So this certificate is kind of like reminding the verifier, and it can check it in log space, all the identities of all the vertices in capital RL. So as it's going along, it's like, oh yeah, 1 is in RL. Oh yeah, 7 is in RL. And what's it trying to do? It's finally trying to check that vertex 9 is not in RL plus 1. So you're in RL plus 1. You're reachable in L plus 1 steps, if and only if there's an edge from an RL vertex to you, to number 9. So the very last thing it checks for each one of these certificates that looks like S can go to vertex number I in at most L steps, that I to, in this case, number 9 is not an edge. Okay, so this piece, as it goes along, it becomes reminded of all the vertices one by one that can be reached in L steps. And what does it do? It checks for each one that you cannot get from that vertex to number 9 in one step. Okay, and that, once it finally does that, it becomes convinced it exactly saw the set capital RL, and that these edges don't exist. It becomes convinced that number 9 cannot be reached in L plus 1 steps. So that's how it can check these kinds of claims too. Okay, that's it. Sorry for going a little over time.